Hello everyone, my name is Gabriel. I'm here with my colleague Parham, and today we're going to present to you the paper called Unsupervised Real Image Super Resolution via Generative Variational Autoencoder. Super resolution is a computer vision technique that aims to enhance the resolution of an image. Two main techniques and two main approaches exist. Here, the authors implement example-based super resolution with patch-based interpolation. The main reasons for these choices are that one pixel contains very little information about surrounding pixels and patterns of the image. However, patch encodes information about surrounding pixels, color distribution, and patterns that repeat all throughout the image, hence taking full advantage of the convolutional neural network's structure. Up until recently, most proposed approaches rely on supervised learning techniques. However, not many datasets exist containing high-resolution images and low-resolution image pairs, so the researchers have to simulate low-resolution images from high-resolution images. However, the results are very far from how real images are normally obtained, where noise, blur, and other degradation factors are present. This sets the table for the contribution of the papers. First, the authors propose a denoising autoencoder that denoises the low-resolution image before doing the super-resolution. Then a super-resolution subnetwork is implemented to enhance the image, which then goes to a discriminator that forces the super-resolution subnetwork to create more realistic images. Here are some related publications that lay the groundwork for the following methodology. The super-resolution technique can be formulated as follows. Let's further define X as a low-resolution image, which is a downsampled high-resolution image with some added noise. Here, we want to approximate the high-resolution image, so we want to maximize the probability of obtaining the low-resolution input given a high-resolution approximation. The problem can be then written as minimizing the distance between the low-resolution image and the downsampled high-resolution approximation. Here is the proposed architecture. At first, a noisy and a clean image goes through the encoder-decoder structure, teaching the decoder a noisy distribution. This distribution is then subtracted from the input at inference time. The denoised image goes through the super-resolution subnetwork and is enhanced. The super-resolution subnetwork consists of 4 residual blocks, the same ones used by ResNet, but without the batch normalization procedure. The super-resolution image then goes through a discriminator and is verified against a reference image. The discriminator classifies the super-resolution image as real or fake. The super-resolution process can be updated by backpropagating the residuals learned from comparing the super-resolution image, which is downsampled, with the input. Here's a visualization of this residual image. A pixel-based mean absolute errors is used as a loss function.
In this section, we are going through the results presented in the paper. The system configurations and training parameters are listed here, as well as the list of employed datasets for evaluation purposes. BSD68 and NTIRE 2090 datasets are used for evaluating the denoising step. The method compared with 4 others in addition to a customized network consists of convolutional neural layers. The result shows that this algorithm provides a higher pitch signal to noise ratio, which means lower distortion. For evaluation of super resolution method, PSNR and perception index are used as evaluation metrics. So we are looking for higher PSNR score, which means lower distortion, and lower PI, which shows better visual quality. The results showed that this method shows better PSNR value but does not demonstrate as good visual quality as SRGAN or ESRGAN method. As we can see here, generally speaking, ESRGAN and SRGAN provide sharper images compared to the proposed method. In addition to the conducted experiments by the author, we also conducted our own experiment to see the applicability of the algorithm in real case scenarios. We explicitly tried to see whether the introduced algorithm can be used in crack detection on concrete structures, which is the subject of our project for this course. Here we conducted an experiment using a DJI M300 drone to record thermal images from relatively high altitude and investigate whether the algorithm can restore the details lost because of the camera's resolution and drone's distance from the object. The experiment showed that indeed it was able to provide much better results, which is critical industrial inspection using imaging systems. In this experiment, we investigate the capability of this algorithm to enhance the details of tiny cracks in a drone-based thermal inspection, and we use a DJI M210 drone equipped with a thermal camera. As you can see, the algorithm improved the image resolution. However, the denoising step removed some of the details regarding tiny cracks. Thank you for listening to our presentation. We are here if you have any questions.